Alright, so in this video, it'll be a continuation of the last one. Topic of this video, the fundamental theorem of calculus. And that is a continuation of the last video I made on the definite integral. So in these videos, I would argue that probably the math is not that bad as far as the problems that I covered. But learning all the concepts and vocabulary, that might be more of a challenge. All right, and that might take time to sink in. It's going to be a matter of memory. All right, so the fundamental theorem of calculus is a way that we can calculate a definite integral. Okay, so I'll pose the question to you. As far as what you've seen or what you know already, how can you calculate the definite integral from a to b of f of x dx? How are you going to do that? Well, in the last video, we learned that you can interpret it in terms of area. And what I mean by that is, so there's this interpretation. If that curve is above the x-axis from a to b, then the definite integral is that area that's contained by the curve in the x-axis from a to b. And then if the curve was below the x-axis, the definite integral is the opposite of the area. So that's what I mean by the area interpretation. There's obviously limits in that because what if you don't know the area? Like, just looking at this, I don't know the area of that. That's not a shape that I'm aware of. It's not a triangle or a circle or a rectangle. So this provides us with a way to calculate definite integrals, but there's serious limits on it that you might not know the name of the shape you're looking at, okay? The fundamental theorem of calculus provides us with a very straightforward way to do this. Here's how you evaluate a definite integral by the fundamental theorem of calculus. You find the antiderivative of that function. You put the upper bound, the upper limit of integration in. You put the lower limit of integration in, and you subtract. That's the fundamental theorem of calculus. It's pretty easy. I mean, it's straightforward. Maybe the numbers get a little out of hand, but that's how you do it. How you do it is fairly straightforward. We learned about antiderivatives in an earlier video, in earlier assignments, and you notice the symbols and notation were similar, okay? All right. And that reminds me, so this is the definite integral. Not to be confused with the, so where was it? Not to be confused with the indefinite integral. Hold on a second. Okay, so we don't want to confuse the definite integral with the indefinite integral. Okay, the indefinite integral, my goodness, I'm forgetting things when I write the slide. So the indefinite integral is the antiderivative. If I look at this, I say, okay, that's the indefinite integral of cosine x, which is sine x plus some constant. All right. You could also call the indefinite integral the antiderivative. All right. But anyway, okay, so that's a side remark that I need to make. Anyway, all right, so this is the definite integral. It's got bounds, it's got limits of integration, and here's a way that we can calculate it. All right, so let's try a problem. So let's do, how about this, just to make a kind of a bridge between what we were doing in the last video to what we're about to learn now. Let's say I want you to evaluate this, and I want you to show that you get the same answer whether you use the area interpretation or the fundamental theorem of calculus. You should get the same answer no matter how you do it. It's math. There's only one answer, okay? So how did we do this by the area interpretation? Maybe make a quick sketch of the graph and see where it is with respect to the limits of integration. So -2, my lower limit of integration, happens to be where this hits the x-axis. So it's a line that looks like that. And like I was saying, it does hit the x-axis over at -2. All right, that's the x-intercept. It hits the y-axis at 8, and if you go over as far as 3, you'll get 20. 4 times 3 is 12 plus 8, that's 20. So not to scale, all right? We'll say that right there, that point, 3 for x, 20 for y, okay? All right, so there's my function. Oops, that's what it looks like with the bounds of integration. Okay? Now, the way I could think about this definite integral is it's the area contained by that line in the x-axis from -2 to 3. And if I look at it from -2 to 3, that would be this. Okay? That's the space contained by the curve, the function, the graph, from -2 to 3 on the x-axis. There it is. It's a triangle. Okay? So the answer to this definite integral is the area of that triangle. So we'll look at it. We'll see. So I found that point to be at 20. So it's 20 units tall. And where was that's 3, right? So 3, and that's 2. So it's 5 units wide. And so the area of that triangle is 1/2 times base times height. And so that's going to be 50. All right. 50 square units. That's the area. All right, so our answer is 50. Okay, so now that's what we learned in the last video. All right, now by making a bridge, I'm trying to show you that that's still okay, but we're learning something new to add to it. So we should be able to do this problem also by the fundamental theorem of calculus. What did it say? So I was just reading my other slide about how the fundamental theorem of calculus works. What do? You find the antiderivative of this. Okay? How you do that, that's been covered in another video. But it's 2x squared plus 8x. All right. That's the antiderivative of this. If you take the antiderivative of this, you get that. So that's an important feature of the fundamental theorem of calculus, is that it relies on you being able to find the antiderivative. Okay? That's how it works. And then we put these bounds in. We put that one in first. So now that I've got my antiderivative, this is what it is if I put my upper bound of 3 in. And then I subtract what I get when I put my lower bound of 2 in. So that's what it looks like all written out. And of course, like, you could do this in your head. If you're good at mental math, you could just get your calculator out and start pressing buttons if you wanted to. But that's what it looks like when you get it down on paper. Okay? All right, so now I'll do the calculations. Okay, and if I do the math, this is 24. Sorry, that's 42. And then minus, and then this is -8. Okay, and then what's 42 minus -8? It's 50. It's 42 plus 8. Well, okay, that's what we got already. I'm just confirming it, and I'm showing you that there's another technique. Okay, so if we had to choose, we'd probably do it this way. This way's probably easier. But if you can't find the antiderivative, then it's not easier. So if you encounter some problem and you just can't figure out the antiderivative, then you're stuck. On paper, you can't do it. Maybe you could figure this other way out. That's one reason why I'm telling you both ways. Okay, so we'll do a few more problems with the fundamental theorem of calculus, but you take your problem, your definite integral, you find the antiderivative, and you put the bounds in, and you subtract, and you got it. That's what you do. Okay? I think all of the trouble, though, that you would have with it would be in finding the antiderivative. So let's do some mixed problems related to that. All right? So let's take this one. Okay? Evaluate the definite integral. Now, I'm definitely not going to even attempt to draw the graph of that and figure out how to look at the area. I'm not even going to go there. We're going to move past that. I'm not saying that you forget about that forever, but right now I'm not concerned about it. Let's do this one with the fundamental theorem of calculus. So first step then, I might say, is find the antiderivative. That's the essential first step. We can't get anywhere with the fundamental theorem of calculus without the antiderivative. So how would you do just this? Antiderivative x minus 5 over root x dx, okay? Now, how you do this, that was covered in another video, and it's not like I'm just going to skip it now, but I won't go through this problem in as much detail as I did in earlier videos, okay? Where I talked about how this is done initially. I will say that I need to break this down into individual terms, okay? Because I've got this rule that says the antiderivative of x to a power, and say the power's n, is x to the n plus 1 power over n plus 1 plus c. So that was one of many rules that I talked about in other videos. And it'd be good if I reduced this one to being like that. So I could do that. I could reduce this to a fraction and see that its individual terms are x over root x minus 5 over root x. Okay, so that's one thing I could do. And then I could reduce each of these. That's x to the first power over x to the 1/2 power. Okay, so that's going to be, if I subtract the exponents, 1 minus 1/2, that's going to be x to the 1/2 power. Okay, and then this is going to be 5 times x to the minus 1/2 power. All right, so there. Now that is something I can work with. Both of these are within the domain of that rule. So this one is x to the 3 over 2 power over 3 over 2. I can carry the minus, the subtraction. I can carry the constant of 5. And with this, I'll get x to the 1/2 power over 1/2 plus c. Okay, so that was the antiderivative procedure. And whenever we found antiderivatives before, we put a plus c. Because if I take the derivative of this, that constant's going to zero out. And I'll get over here, okay? So, all right, finish it up. So I get 2/3 x 3 over 2. What's 5 divided by 1/2? That would be 10 x to the 1/2 plus c. All right, so I've got my antiderivative. So that brings me to my second step. Okay, now that I've got that, I understand that the definite integral from 1 to 9, x minus 5 over root x dx is going to be 2/3 x 3 over 2 power minus 10 x 1/2 power evaluated from 1 to 9. Okay. All right. Now at this point, you might be wondering or thinking to yourself, why don't we include the plus c down here? If the fundamental theorem of calculus says to use the antiderivative of that, where did the plus c go? Well, we can use any antiderivative, meaning an antiderivative to this is 2/3 x 3 over 2 minus 10 x to the 1/2 plus 7. If you take the derivative of that to check it, the 7's a constant and it's going to zero out. Or you could say it's 2/3 x 3 over 2 minus 10x to the 1/2 power minus 6. That constant can be anything. So anything like this plus a constant is an antiderivative. So we think like this. Since you can use any antiderivative, any one of them, then what if the c was 0? That's one of the antiderivatives. So we just considered that the c is 0, all right? Or we don't worry about it. Okay, that's the long answer. Short answer is you don't have to put the c down here, all right? It's not going to matter. Okay, so I've got it then. I've found my antiderivative. Now I got to put 9 and 1 in, right? So first I put 9. This number goes in first. So I'll get 2/3 times 9x to the 3 over 2 power minus 10 times 9 to the 1/2 power. Okay, so I've got to figure out what that number is. And then I subtract. So I put 1 in. 2/3 1 3 over 2 power minus 10 1 to the 1/2 power. Okay, so that's what I'm up against now. So let's see, that's 3 over 2 power. That would be the square root of 9, which is 3, to the 3rd power, which is 27. Divided by 3 is 9 times 2 is 18. So that's 18 That's the square root of 9, which is 3 times 10. So that's 18 minus 30 for that number. Okay. For this number, 1 to the third of 2 power, that's the square root of 1 to the third power. So that's 2/3. And then minus 10. All right. So this is going to be negative 12. And then negative 2/3 minus 10. Negative 2/3 minus 30/3. So that's negative 28/3. Okay, so that'll be negative 12 plus 28/3. So that'll be negative 36 plus 28 over 3. So that'll be negative 8/3. Okay. All right, so negative 8/3. That's it. That's what we get. All right, so let me do this. I got my steps, and I wanted to make sure you could see the individual work for the steps. Let me just take this and put up here. So I want my answer to stand out and be direct to the question. So even though I did all this stuff there, I'll say, well, the answer is negative 8/3. Okay? All right, so that's how the fundamental theorem of calculus works. You'll probably get stuck on this. All right, I did this in my head, but I think most people would do it in a calculator, whatever. Do it how you want. You probably won't get stuck here, though, because that's just calculations. All right, if you need help figuring out how do you do 9 to the 3 over 2 power, I can elaborate a little bit right now, but let's say fractional exponents are understood like this. 9 to the 3 over 2 power is the square root of 9, then raised to the third power. The square root of 9 is 3, and 3 to the third power is 27. So I got 27. I divide that by 3. That's 9 times 2 is 18. Okay? All right, so I got negative 8/3. Let's try another one. So let's do this one. Okay? So evaluate the definite integral. Now it's like maybe we know what to expect. We know how we're going to end up doing this. Okay? Meaning that we're just going to take the antiderivative and we'll figure that out, but we'll put 2 and 9 into it. We'll put 9 first and we'll put 2 second. We'll get our answers. We'll subtract them and that'll be it. That's how it's done. Okay? We just need that antiderivative. That's what might be the hard part about this. So let's see. How would you find the antiderivative? Okay, how do you do that part? So just think about it like this. Without the limits of integration. 1 over root 8x plus 9. Let me write it this way. Let's say 8x plus 9 to the negative 1/2 power dx. Think of it like that. How do you do that problem? This is a U substitution problem. Okay, that's something covered in another video, but that's how you find the antiderivative this time. When I say U substitution, if you can think back to that other video, if you've at least seen it and worked out assignment, you remember a little bit about it. It's that this problem becomes like this with the substitution. Okay, we're going to make a substitution. We're going to choose that U is going to be something, and it's going to turn this into that, and then we'll know how to work it. All right? So what should you choose U to be if you think you can turn this into that? Well, 8x plus 9. That's what? Okay? Now, we've got to incorporate U and du. So when we choose this, our next step is to say du is, what's the derivative of this? 8 dx. And then I want to substitute these. And I notice I see dx, I don't see 8 dx. So I divide both sides of this by 8. And I get like that. And now this one and this one can fully substitute this in terms of u instead of x. Okay. So all right here, I'll make my substitution. So, okay, I'll get, that's u, right? U to the minus 1/2 power. And then dx, so that's going to be du over 8. Okay. Now we got that basic. What about the 8, though? I mean, I didn't say there'd be an 8. Like, here's our basic formula right here, where I see the variable to an exponent, and I add 1 to the exponent, and I divide by that same number. That's the technique when you get to this point. What about the 8? Well, so that 8 there is actually a 1 over 8. Okay? In which we can factor out. You're allowed in definite or indefinite integrals to remove constant factors. So that's a factor of 1 over 8. It's like u to the negative 1/2 power times 1 over 8 times du. We can remove the 1 over 8. Okay, now I've got it. My answer is 1 over 8 to carry that constant down. And what is our formula for this? We add 1 to the power, so negative 1/2 plus 1. And we divide by that same thing, then we do plus c. And we will get 1 over 8. So what's this? U to the negative 1/2 plus 1. That's u to the 1/2 power. And what's this? That's also 1/2 plus c. So two things. This is 1/8 times 2. When I divide by 1/2, that's the same thing as multiplying by 2 over 1. So if I take 1/2 times 2, that's 1/4. Okay? And this is u. All right, u is 8x plus 9 plus c. Okay? There's my antiderivative. All right, that's what I needed. All right, that's what I needed. So here goes. I'm going to go back up here. Okay, I needed the antiderivative. So, all right, I got 1/4 root 8x plus 9, 2, and 9. Okay? So let's now I'll do the math, a little bit of the math in my calculator. I'll write down what I get, but there's the antiderivative so far. All right, so with 9, we'll get root 81, 1/4 root 81, and with 2, we'll get 1/4 root 25. So, well, this is going to be what? Root 81 is 9, so that's 9/4 minus root 25 is 5. That's 5/4. 9/4 minus 5/4 is 4/4, and that's 1. All right, so all that work, and it's just 1. That's how it goes, though, sometimes. Okay? All right, well, we got it. So there's lots of stuff here. I mean, but I would say the definite integral from 2 to 9, 1 over root 8x plus 9 dx is 1. That's its answer. That's its final calculation. Along the way, I emphasize, you got to know how to find this. You got to know how to use the rules. If you need to use u substitution, we'll need to recognize that. So on and so forth, okay? Take some practice to learn how to do everything. But, all right, that's another example. So let's see. Let's do one more like this. Okay, what about this one? Evaluate the definite integral. Well, so, I don't know. Let's try to get some perspective on this. When I did this one, the antiderivative, I did it by this rule right here. I had to reduce it a little bit. I had to do some algebra, but ultimately that's the rule that I used. Okay? And then this one, well, that was a different technique. That was u substitution. Okay? What about this one? Well, this one again, this one will be different. Now, the overall strategy is the same, and that's that I need to find the antiderivative and evaluate it between negative pi over 6 and pi over 6. So, yes, I got to do that. But how you find that, how you find the antiderivative on this problem is different than the other ones. Okay? And I would say easier. What do you think about this? Let's do 5 times tangent. 5 times tangent of x. Negative pi over 6. Pi over 6. Would that be it? What's the derivative of tangent? It's secant squared. What's the derivative of 5 times tangent? 5 secant squared. Okay? So very easy to find this time. There wasn't a technique or some elaborate algebra that I need to use. It's just a matter of fact that the derivative of tangent is secant squared. All right, it's that simple this time. All we needed was the antiderivative, right? Doesn't really matter how you find it. It might be different every time. Okay, so now that I've got that, I have my antiderivative of 5 secant squared. I do 5 times tangent of pi over 6 minus 5 times tangent of negative pi over 6. Okay? All right, so tangent, so that's 30 degrees. Tangent of 30 degrees is root 3 over 3. So let's do 5 root 3 over 3. Okay, for that one. And then this one, tangent of negative 30 degrees, or tangent of negative pi over 6, that's negative root 3 over 3. So this is going to be, like I'm subtracting, but the calculation there is going to make it negative 5 root 3 over 3. Okay, so that will amount to adding. I'm subtracting, but this calculates to be negative 5 times root 3 over 3. So, all right, we get 5 root 3 over 3 plus 5 root 3 over 3, right? And then those are fractions with common denominator. I can add the tops. That's 10 root 3 over 3. Okay, and then there's our answer. So hopefully then we've seen enough for you to practice. You've seen a little bit of everything. But there's the common thread, right? If there's like anything that stands out about the video in this particular lesson, is that you'll need to find the antiderivative in order to evaluate a definite integral. Okay? All right. So 3 examples. Let's do one more real quick problem to try to tie everything together. All right, so for this example, suppose I give you a scenario, all right? And I just want you to think about the scenario a little bit before I work it. So say I just present the problem to you this way. Okay. So here is a curve right here. Y is equal to x squared. And suppose that this is 1 and that this is 3. Okay. Can you tell me the area right here? Okay. So my problem to you, my question to you right now for you to think about is, can you calculate this area? Or measure this area? Tell me how much space there is right there. Okay? Now think about the ways that we've done problems like this. Like say I'm going to go back to this one. Can you tell me that area right there? Well, this is a line. And so that makes it fairly straightforward. The fact that this is a line makes the area contained by those limits of integration with respect to this line to be a triangle. And a triangle is a familiar shape to us. Its area is 1/2 base times height. It's probably no big deal to do that, all right? This is curved though, so that's the fact that that's curved changes everything. It's not a trapezoid, it's not a triangle, it's not a rectangle, it's not anything that we have a name for, okay? But can you put it all together, all right? Isn't it true that that area would be the definite integral from 1 to 3 x squared dx? Okay? Is that accurate? That is true. Okay, that is definitely the case. That this is the same thing as the area there. They mean the same thing. And if you can calculate this, then that's a way to calculate or measure this area. Okay? So that's my first step, is like, do you realize from what we've been learning that that's true to start with? How would I know that? Well, it's like, you know, there's a lot of stuff covered in these videos and in this last assignment, but from this, that's just one of the interpretations of the definite integral that I gave to you, okay? At another time, I told you about that. I've been emphasizing it since then. So say we can start there. Now that you get here, how do you calculate this? Well, that's the fundamental theorem of calculus. the topic of this video gives us a pretty easy way to evaluate that. Here's what you do. Now that you got it down and you know that's what you want to figure out, we find the antiderivative of it, which is like so. We evaluate it from the bounds 1 to 3. We put 3 in first. We'll get 3 third power is 27 over 3 is 9. And we put 1 in second. Third, so 9 minus 1/3. It's going to be 26 thirds. Okay. So the area right there is 26 thirds square units. All right. Now I haven't been using units because I'm really trying to focus on just the math, but I don't know. How about this? I should at least make brief mention of the units. Suppose this graph was made to scale, and this was 1 foot, and that was 3 feet, and so on. And say we did all of our markings by feet, all right? Every single mark on the graph was 1 foot. Then this would be 26 thirds square feet big. All right, so yes, the area does have units to it. It's not just a number. But as far as the technique goes, that's the number that you get. And if we have units, we can incorporate the units too. Okay, so in one problem, this ties lots of different things together. You understand what area looks like and how to think about that. The relationship of the definite integral to area measurements, that's another thing. And then how you calculate the definite integral once you have it down. All right. All in all, it gives us a way to make a measurement.